Okay, this is chapter 7 homework for Physics 101. This first problem is really just sort of figuring out what are the variables and then plugging them into the right equations. I'm just going to write the equations up here for our kinematics equations for circular motion. That is that theta equals theta naught, which is usually 0, plus omega naught t plus 1/2 alpha t squared. And our other is omega, or omega final, the final angular speed, is equal to omega naught plus alpha t. Alright, so a propeller whose arm length is 1.2 meters, that's r, is equal to 1.2 meters, starts from rest, so omega naught is equal to 0 radians per second, and begins to rotate counterclockwise with a constant angular acceleration of 2.7 radians per second squared. So that's my alpha, and since it's counterclockwise, alpha is positive, and it's equal to 2.7 radians per second squared. This should be a subscript right here, or a superscript. And then I want to know how long does it take for the propeller's angular speed to reach 5.7 radians per second. So my omega final is equal to 5.7 radians per second. And then in part A, I just want to know how long does it take to reach that. Right, I know omega final, omega initial, and I know alpha, so I just go with this second kinematics equation and I solve for t, and t is equal to omega final minus omega naught, omega initial, divided by alpha. So putting in my numbers there, I have 5.7 radians per second minus 0 divided by 2.7 radians per second squared, and that gives me a value of 2.1 seconds. So it requires 2.1 seconds. And in part B, how many revolutions, that is, I want to know what is theta, does it take for the propeller's angular speed to reach 5.7 radians per second. So now I know the time required to reach that speed. I want to know what is the displacement, the angular displacement. I'll first have to calculate it in radians, and then I'll have to convert that into revolutions. So theta is equal to omega naught t plus 1/2 alpha t squared. That's taking my initial position to be 0, as is usually the case. So that's equal to omega naught, which is 0 times t, so I'll just leave that out, plus 1/2 alpha. The angular acceleration is positive 2.7 radians per second squared, and then my time is 2.1 seconds from part A. That's squared. That gives me a value of 6.0 radians. Now it asks specifically for the answer in revolutions, so 1 revolution is equal to 2 pi radians. 6 over 2 pi is roughly 1. It's 0.95 revolutions. 0.95 revolutions. Part C, what is the linear speed of the tip of the propeller? Alright, we can convert linear speed to angular speed to linear speed just by multiplying by the radius. So the linear speed is equal to omega times r. The omega at that point is 5.7 radians per second, and the radius of your arm is 1.2 meters, or the moment arm, the length of the moment arm, or the radius of the motion rather, is 1.2 meters, and so that gives me 6.8 meters per second. Now, in part D, what is the linear acceleration of the tip of the propeller at this point? The linear acceleration, in a similar way as the linear velocity, is just the angular acceleration times the radius. The angular acceleration is 2.7 radians per second squared times 1.2 meters, and so that's equal to 3.2 meters per second squared. And then finally, in part E, what is the centripetal acceleration? I'll call this AC, or you might call it AR. The centripetal acceleration is equal to v squared over r. Alright, I already know the linear velocity, that's that v value. I found that in part C, so it's 6.8 meters per second squared over 1.2 meters. Plugging that in, I find that it's equal to 39 meters per second squared, or I can find it this way. The centripetal acceleration is v squared over r, but I know, as an aside, that v is equal to omega r. So I can just plug that in. So it's omega r squared over r, which is omega squared r. So that's an alternative definition for the centripetal acceleration based on the angular velocity instead of the linear velocity, depending on what you have. So omega squared r, omega at that point is 5.7 radians per second. Squared times the radius, which is 1.2 meters, and that gives me 39 meters per second squared, which is the same as we had up here. So those are all the answers. Potter's wheel moves from rest to an angular speed of 0.2 revolutions per second in 30 seconds. We know its angular acceleration in radians per second. That's in radians per second squared. Let's just write down what I know. I know that my initial speed says that it's rest, so initially omega naught is 0, or omega is 0. And it's moving in a time of 30 seconds, and it increases in speed to 0.2 revolutions per second. But I know I want my answer in radians per second, so I'm going to go ahead and convert this to radians. In general, you're going to convert your revolutions to radians. You can't really go wrong with that unless it specifically asks for revolutions. 2 pi radians is 1 revolution. So doing that conversion factor gives me 1.3 radians per second. And I want to know what is alpha. I know that omega final equals omega naught plus alpha t. That's one of my basic kinematics equations. So I want to solve for alpha. That's omega final minus omega naught over t. Omega final is 1.3 radians per second minus 0 divided by 30 seconds. And that gives me a value of 0.043 radians per second squared. A dentist drill starts from rest. After 3.2 seconds of constant angular acceleration, it turns at a rate of 2.51 times 10 to the 4th revolutions per minute. What is the acceleration, the angular acceleration, and the angle through which it rotates? So first let's write down what we know. Omega naught is equal to 0. Starts from rest. Time is 3.20 seconds. Our omega final is equal to 2.51 times 10 to the 4th. This is in revolutions per minute. So I'm going to go ahead and convert it. In 1 revolution, there are 2 pi radians. And in 1 minute, there are 60 seconds. That gives me the omega final in radians per second now is 2630 radians per second. Now for part A, I want to know what is alpha equal to. I know that omega final equals omega naught plus alpha t. So alpha is given by this, which is 2630 minus 0 divided by t, which is 3.2 seconds. And that gives me 822 radians per second squared, 822. And then in part B, I just want to know what is the angle. That's equal to theta naught plus omega naught t, 1/2 alpha t squared. But our initial position be 0. So putting in the numbers here, and then omega naught is also 0, so it's just 1/2 times alpha, which is 822. Times our time squared, 3.2 seconds squared. My seconds cancel there, and I get 4210 radians. Certain light truck can go around a flat curve having a radius of 150 meters with a maximum speed of 32 meters per second. What maximum speed can it go around with a curve having a radius of 75 meters? So our curve is getting a smaller radius, so it's going to have to go slower because it's a sharper curve because it has a smaller radius. This is a picture of what we have here. I have this truck. This is from above. Here's our truck. Some wheels on it. The force that keeps this truck on the road is the force due to static friction. And that static frictional force, that is the force between the tires and the road, and it's static because the tires, the rubber of the tires don't move with relation to the road. Only if it's skidding. If it's skidding across the road, then it's kinetic friction. But with the tire rolling, it's static friction. So that static frictional force provides the force that keeps the truck on the road and actually causes it to go in this circular path. So that static frictional force then is the centripetal force. So it acts towards the center, the centripetal force, and it is provided by the static frictional force. The static frictional force is the centripetal force. So I can write that Fc is equal to Fs. That is mv squared over r is equal to mu static times force normal. And in this case, the car is not on an incline, right? It's just flat on the road. It says it goes around a flat curve. That means that the normal force then is going to equal the weight of the object. So I can make this mv squared over r, and that's equal to mu s times mg. Let's take in a little aside here because this is kind of important. If I have a truck, it's my truck from the front. If it's on a flat curve, then the normal force is equal to the weight. Alright, and so the normal force then is maximum what it's supposed to be. But usually when they have these sharp curves, they put them on a bank, like if you're coming off the interstate or whatever. They put them on an inclined plane. So now this is my car. Alright, I still have the same weight. Alright, so my normal force then is reduced. It's smaller because there's only a component of the weight that's actually creating the normal force. So why would they then put the curve on an incline like that? Well, because on the incline, the static frictional force here, let's say we'll call this Fs inc, is smaller than the static frictional force here. So Fs inc is less than the static frictional force on a flat road. So if you're reducing your static frictional force because you've reduced your normal force, what are you gaining? Well, what you're gaining is, see, the static frictional force is pulling in this direction. It's opposing the motion because you want to go up. So that acts as your centripetal force, but you also have an additional force, and that's the component of the x component of the weight. And so that adds an additional force that factors into your centripetal force. Alright? But in this problem, we have this scenario. So let's return to this problem. I want to know, I need to know what is mu s. My m's cancel. The mass of the truck doesn't matter, so that's good for the roads because you don't have to give different minimum speeds for different types of cars. You can just give the same minimum speed based on some value for mu s. So solving for mu s is equal to v squared over rg. V is 32 meters per second squared over r, which is 150 meters, and 9.8 meters per second squared. That gives me my value for mu. That's 0.70. Now that value for mu is based upon the tires that you have on your car and the state of the road. Is it dry? What's the road made out of, and what have you. It doesn't change if the radius of the curve changes, and that's really what this question is asking. What if now we have a radius of 75 meters? What then is your maximum speed that you can go around? So we can start with this equation right here. That is mv squared over r is equal to mu s mg. But now instead of solving for mu s, I'm solving for v. So my maximum speed is equal to the square root of mu s g r. That's the square root of 0.7, which has no units, 9.8 meters per second squared. And then r now is 75 meters. And that gives me a value of 23 meters per second, which is less now than the maximum speed on the bigger curve. So that's the answer. That's about 50 miles an hour, roughly. Alright, a drill bit rotating at 3,600 revolutions per minute rotates through 50 revolutions while coming to rest. Find the drill's angular acceleration. Let's write down what we know. Alright, so omega naught is equal, that's my initial speed, is 3,600 revolutions per minute. Omega final, it's coming to rest, so it's 0. I want to know what is alpha, and I know that in the time that it takes to come to a stop, it goes through 50 revolutions. I'm just going to keep everything in revolutions per minute, revolutions and minutes, just for kicks. You know, you don't have to convert, or you don't always have to convert to radians, but so in this case I'm not going to, just to see what the different numbers fall out as. So I'm going to write my two equations. I have theta equals omega naught t plus 1/2 alpha t squared, and then I also have omega final equals omega naught plus alpha t. Now in both of these I have two unknowns, and those two unknowns are alpha, the angular acceleration, and the time. And I want to figure out what is the angular acceleration. I'm going to do this by substitution. I'm going to solve this equation for t. I know this is 0, so t then is equal to negative omega naught over alpha. Now I'm going to take this, which is the same as t, and I'll plug it in there, and I'll also plug it in there. So this equation now becomes theta equals omega naught times negative omega naught over t. That's the same as, over alpha, excuse me. That's the same as t, plus 1/2 alpha negative omega naught over alpha squared. So this gives me negative omega naught squared over alpha plus 1/2 omega naught over omega naught squared over alpha. I factored out one of those alphas. And so that is equal then to, let's see, I have negative 1/2 omega naught squared over alpha. That's theta. Now I can solve this for, I want to know what is alpha. So I'll just solve this for alpha. So I have alpha is equal to negative 1/2 omega naught squared over theta. That's negative 1/2. Omega naught is 3,600 revolutions per minute. And that's going to be squared divided by theta, which is 50 revolutions. And that's going to give me my final answer in revolutions per minute squared. So let's see, I have 0.5 times 3,600 divided by 50. Oh, 0.5 times 3,600 squared. I get 1.3 times 10 to the 5th. Negative 1.3 times 10 to the 5th. That's in revolutions per minute squared. And now we can make this conversion into radians per second squared. So I have negative 1.3 times 10 to the 5th times 1 revolution, 2 pi radians, 1 minute, 60 seconds. That has to be squared to get rid of the minute squared. And I get a 230 radians per second squared. Negative 230. So either one of these would be right in this particular case. But again, in general, you want to convert all your revolutions in minutes to SI units. But in this particular case, you do not have to. A boy swings a 15.7 kilogram stone in a horizontal circle with a radius of 0.98 meters. The string breaks under 370 newtons of tension. What is the maximum speed in meters per second that the stone can have? Alright, so I have this situation of the stone is traveling in a circular path, and what's causing it to go in that circular path is there's a kid has a string tied to it. There are a couple forces acting on here. We have the tension in the string provides the centripetal force that causes it to go in a circular path. So Fc is equal to Ft, and so that's Fc is mv squared over r, and then that's equal to my tension. So I want to know what is V, so I can just solve this equation for V, and that is the square root of Ftr over m, which is the square root of 370 newtons, times r, which is 0.98 meters, over m, which is 15.7 kilograms. If I put in those numbers, I get 15 meters per second. A sample of blood is placed in a centrifuge of radius 15 centimeters. The mass of a red blood cell is that value, and the magnitude required for it to settle out of the plasma is 4 times 10 to the minus 11 newtons. How many revolutions per second should the centrifuge be operated? Alright, so I know that Fc, my centripetal force, is mv squared over r, and this is the force that's going to be acting on the blood as it goes around in the centrifuge, and it's going to cause it to settle out. Now I know that V is equal to omega r, so I can make that substitution and say Fc then is equal to m omega r squared over r, excuse me, and so that's equal to m omega squared r. And now I want to solve for omega, which is Fc over m times r. I'm putting in my values here of 4 times 10 to the minus 11 divided by 3 times 10 to the minus 16 kilograms. That's the mass of your red blood cell, divided by the radius. It was 15 centimeters. That's 0.15 meters. So that gives me an omega of 940 radians per second, and then I want to convert that to revolutions because the question requested that. There are 2 pi radians in 1 revolution. That gives me 150 revolutions every second.